Welcome to CS70 Spring 2018 Discussion 11B, Problem 2. Problem 2 talks about the sum of independent Gaussians. The result that we're going to prove is that if we take the case of two independent Gaussian random variables, their sum is also a Gaussian random variable. Compare this, for example, when the case you take is of two independent uniform random variables, one from 0 to 2, the other from 1 to 3. Even if these are independent, the sum is not uniform in 0 to 3. However, we'll see that for Gaussians, this property does in fact hold, and all it requires is independence. Okay, so the setup is as follows. We have capital X and capital Y to be standard normal random variables, and they're independent. Remember, a standard normal random variable has zero mean and unit variance. Now we have an expression for its PDF, and what we want to compute in part A is the joint density, i.e. we want to calculate this quantity for x and y. Now remember, if x and y are independent, by definition, this becomes the product of their marginal distributions. And this we now know is 1 over root 2 pi e to the negative x squared over 2 times 1 over root 2 pi e to the negative y squared over 2. And finally, this is 1 over 2 pi e to the negative x squared plus y squared over 2. Okay, that was part A. Before we start part B, there is one observation we need to make about a standard normal random variable, which is if you were to plot the density curve, it looks like your standard bell curve. In particular, it depends on x squared, which implies that f of x is equal to f of negative x. So there is symmetry about the origin, and for a general Gaussian random variable, there would be symmetry about its mean mu. Now we will notice that in the two-dimensional setting, i.e. fxy, there is even more symmetry. So now we see that fxy is 1 over 2 pi exponential of x squared plus y squared over 2. So notice, not only is this symmetric for negative x and for negative y and y, for any combination where x squared plus y squared equals r squared, i.e. for anything on a circle, the PDF has the same value, which in particular implies that if you were to plot this, say in 3 dimensions, not only would you get symmetry of this form, everything in this region would have the same height. Why is this good? We'll see that going forward. All right, part B is sort of taking us on a sidestep, which talks about just a Cartesian plane and says, what does the region little x plus little y less than or equal to some constant c look like? Okay, so let's just plot that. This is not specific to random variables, just for some line in our space. Notice the point c comma 0 satisfies this line on the equality. The point 0 comma c satisfies this, and this is linear, so 2 points uniquely determine this line. Further, the region I'm interested in must contain the origin, because 0 plus 0 is less than or equal to c as long as c is positive. So then the region I'm looking for is this one. That was part B. Okay, now let's talk about part C. Remember, in part B, we had the setting x plus y less than or equal to c gave us this region. Why do we do this? Well, in our next steps, what we're going to say is that the probability that x plus y is less than or equal to some c will correspond to the integral of the joint PDF over this entire region. Let's call it R. in whatever abstract sense, I don't compute that integral, but it will be represented by this thing, right? OK, now let's look at part C. So in part C, it says, look, this region can also be thought of by rotating our axes by 45 degrees. Why do we do this? Because x plus y equals c makes an angle of 45 degrees with my standard basis axis, and I want to make this a perpendicular line. So now if I rotate it by 45 degrees, I get a line like this. Let's call this x prime and y prime. Remember, all I did was I took these two axes and I rotated it this way by 45 degrees. Once I do this, I notice that this distance will now be c over root 2. To see why that is true, let's just look at the triangle given to us by this particular region. This was the old axis, and what I now have is an axis of this form, where this corresponds to a pi over 4 rotation. And then I'm going to use Pythagoras' theorem, where if this side length is c, this side length is c, then the hypotenuse must be c times root 2. And just this much must be half of it, so it will be c over root 2. And now this distance, again by Pythagoras, will be c over root 2. And that's exactly the distance corresponding to this guy. OK, so then in my rotational figure, this region R corresponds to this region over here, where my old axes looked something like this. Now let's talk about part D. Part D says that, well, you rotated your axes, but you've already concluded that x and y are rotationally symmetric, which means if this was your axes and you rotate them, the density that you will get corresponding to this rotation is the same as the density without the rotation, right? Which would tell us that in particular, x prime and y prime would have the same distribution jointly as that of x and y. Why? Because these are just rotations of each other, and we just showed earlier that the joint density depends only on the sum of squares. So in particular, for a rotation, it is symmetric. Okay, well then the event that x plus y less than equal to some c corresponds exactly to the event that just x prime less than or equal to c over root 2. Just the way we've set up our regions. Well then, this must be the same as root 2 x prime less than or equal to c. However, we had said that x prime has the same distribution as x. In particular, this is a normal on 0 and 1, which tells us that root 2x prime is then normal on 0 and 2. Side exercise to verify this. Remember, think back to question 1 and apply what we did using a equals root 2 and b equals 0. OK, well, if this is true, this implies that x plus y is a normal on 0 and 2. OK, and so when x and y were normal 0, 1, we saw that x plus y is normal 0, 2. However, it can be shown by a very similar analysis to what we just did, that let x be normal on some mean with some finite variance, let y be normal with some mean and some finite variance. Well then, intuitively what you think is correct, which is that x plus y is normal with the sum of their means and the sum of their variances, as long as these two are independent. Remember, independence was key in our argument in making that the joint density was rotationally symmetric. OK, now let's talk about part E. So part E talks about a special case of the central limit theorem. And remember, the central limit theorem states that if you take n IID draws from some distribution, where each of your draws is identical and independent of each other, then the sum of your draws will resemble your expectation very, very likely. And in particular, S sub n, which is defined to be this quantity, which is just the sum of n entries divided by n, will tend to a normal distribution with the mean and the variance changing with 1 over n. Now, the proof of this is beyond the scope of CS70. However, we will prove this for a special case when each of the x sub i's is normal with some mean mu and some finite variance. Remember, the CLT holds no matter what the distribution of each of the x sub i's is. Okay, so in this case, using what we saw earlier, we can conclude that S sub n, so n times S sub n, which is the sum of each of my x sub i's, using an induction argument on part D, we can say that this must be normal on n times mu with variance n sigma squared, which in particular implies that ns sub n minus n mu will be normal on 0 and n sigma squared. And finally, that s sub n minus mu would be normal on 0 and sigma squared over n, where in this last line, I have used the jump that if I divide by n, the mean of 0 is still 0, but the variance changes by a factor of 1 over n squared. And that's exactly what part E tells us.